Welcome to our first BayesiaLab webinar of 2025. It's a great pleasure to welcome so many of you to our event today. When I last checked this morning, we had well over 400 registrations, so we are thrilled to see such a great interest in our webinar topic today. The topic we are presenting today significantly expands the range of applications of Bayesian networks and BayesiaLab. And please allow me to put this into context using a diagram which many of you have seen before. It shows the BayesiaLab workflow with a conceptual Bayesian network at the center. In many webinars and seminars over the years, we have showcased use cases which are shown on the right side of the diagram. They all relate to decision support and include analysis, simulation, diagnosis, optimization, and risk management. Moving to the left of the Bayesian network at the center, we see the sources of knowledge that we can use to generate Bayesian networks. With BayesiaLab, we create a Bayesian network by modeling expert knowledge or performing knowledge discovery through machine learning. And this is what the previous iteration of this diagram showed. What's new in this chart is that BayesiaLab can now also tap into generative AI and retrieve any available knowledge. For that, we have developed Hellixia, BayesiaLab's new subject matter assistant, and GenAI Partner. Let me now introduce today's topic very briefly. And you may be familiar with the general topics through our seminars and webinars and papers that we have produced about key driver analysis. All of these studies have been based on numerical and categorical survey data. This has allowed us to develop complex probabilistic structural equation models, which could then be used for product optimization, for instance. Today's case study is quite different. Instead of structured numerical data, we have unstructured textual feedback from consumers that we wish to evaluate. However, our objective remains to obtain a Bayesian network model to perform simulations, just like we've been doing in the context of key driver analysis. This is where Hellixia, our BayesiaLab's new subject matter assistant and GenAI partner, comes into play. And how this works, you'll see over the course of the next hour. But before we start, let me just mention that we have a Q&A panel that you should see on your webinar screen, where you can submit your questions. However, given the amount of material we are presenting today, we probably won't have time to answer all of them. However, we'll record all your questions and get back to you individually. Now, I'd like to extend a very special welcome and introduce you to my friend and colleague, Dr. Lionel Jouffre, who is dialed in from Bayesia's headquarters in France. Lionel is the CEO of Bayesian, and Hellixia is his brainchild. So there's no one who would be better qualified to tell us about this innovation in Bayesian networks. So now it's time for me to hand over the meeting controls to Lionel. Lionel, the virtual stage is yours.
So yes, thank you, Stefan, for the introduction. So today I'm going to talk about using Hellixia for transforming textual feedback from consumers into causal Bayesian networks. So this is something that we were unable to do 2 years ago, but even few months ago now, but now we found a solution to try at least to extract some useful knowledge, right? So Stefan already spoiled a little bit my intro because I'm using this diagram to explain what we are doing. So since 25 years, we are creating Bayesian networks. So Bayesian networks it's a one of the main pillar of AI. Even though since 2 years we are talking only about generative AI, but well, this is not. This is a huge field, but still. So this is a Bayesian network are directed acyclic graph, right? And as I said, this is the brain of our expert system, and we are creating this Bayesian network since 2001. So we created Bayesian for that purpose, for proposing a new software that allows to machine learn automatically Bayesian network by analyzing structured data. Right. So we were one of the first team to do research on structural learning for Bayesian networks. But historically, Bayesian networks have been were created by using expert knowledge. So the idea was to use your knowledge and manually create the nodes, the states, and the links, and then try to find the best distribution to associate with all these nodes, right? And once we have that, we have a compact representation of what we call the joint priority distribution. So we are using these two approaches since 25 years now, but since 2 years, we can also exploit the power of GenAI. And so in January 23, we have started to develop Hellixia. So Hellixia is our subject matter assistant that allows us to bring some external knowledge, right? So it's super useful for, helping me when I'm doing brainstorming session. The very first idea of Hellixia was to help me understand the field, to extract dimension, to help the experts to build the best Bayesian network as possible. And then we have added some features to also help, machine learning. So at the end of the day, these three sources of knowledge are used now all together for creating Bayesian networks, right? So this is for the qualitative part and also the parameters. And once we have a fully specified Bayesian network, then we can do decision support. And Stefan already mentioned that, right? So, but as you can see, one of the strengths of Bayesian network is the qualitative structure, the graph. So I'm going to show you what we have done with Hellixia, but some of the features of Hellixia are just focusing on the qualitative part, which means that we don't go to the right side. We don't use probabilistic inference. We just stay at the graph level, and still we have lots of knowledge that is brought by Hellixia. So let's talk about Hellixia, the features that we have created since 2 years. So there is one of the first blocks that we have now is what we call the automatic tool. So this allows you to you have a window where you enter your question, and by analyzing this question, we just create a causal network or a semantic network. So here the color coding, when it's gray like that, it means that this is not a probabilistic network. So this is purely qualitative. Then we added a block for being able to analyze documents, right? So this is something we added 3 or 4 months ago. So by associating a knowledge file with Hellixia, then we can create semantic flowchart, causal semantic diagrams, knowledge graph, but also causal networks and semantic networks. So again, in gray, this means that we are just using the qualitative part, and when it's not gray, so this is really a Bayesian network. So this can be done by analyzing just the knowledge file, but we can also trigger Hellixia features by using the nodes, right? So, a node has a name, has a long name, can have an associated comment, and also a knowledge file. So by using the nodes, we can also, run or develop semantic flowchart, causal semantic diagrams, knowledge graphs. So this allows to understand a domain. We can also find entity relationship between nodes that represent entities of the domain, so they are not probabilistic relationship. We can also try to find a verb that qualifies this relationship. And then when we switch back to Bayesian networks, we can create automatically causal networks. We can find causal relationship between nodes that are already there. We can have now a multi-engine causal relationship, so which means that we can run in parallel use in parallel different LLM engines. We can use them for finding or estimating causal structure priors. We can also find pairwise causal link between pairs of nodes. We can also use Hellixia for elicitation, right? So we can use it for finding what are the dimensions we need to include when we do brainstorming. So we start with a target node, a question, and then we can obviously use the experts that we have in the team, but also use Hellixia for trying to find dimensions that the expert forgot, for example. And we can also, in this elicitation section, use the Hellixia for finding, estimating priors of the root nodes, and also estimating the local effects associated with the nodes. I'm going to go through that in a few minutes. We can use Hellixia for generating data, so at the end of the day, this is creating embeddings for capturing the semantics associated with the nodes. And we can use it for doing lots of things on the commands that are associated with the nodes. So we can create automatically a command that will contains a set of keywords by using the keywords that we are also using for the dimension elicitation. We can also create a command that will directly define the concept that is behind the name of the node. We can use Hellixia for condensing or elaborating the comments of the nodes and arcs. And we can also generate a long name that will be the summary of the comment that is associated with the node. We can use it for associating automatically a name with classes, so very useful when we do probabilistic structural equation models, so when we have hierarchical models with latent variables. So usually it's quite difficult to find a name, so here Hellixia can help you for that. We can use it for variable clustering. And the last part is for generating images that allows you to have nice Bayesian networks that you can use for communication. We can use it for translating and also for generating textual report of the analysis of the network, right? But today, I'm going to just use these two blocks, so document analysis for creating semantic, causal, and knowledge graph, and also a causal network. And then I'm going to use the green part for the elicitation of our ICI model. And the example I've chosen, even though it's not really a choice, I had to work on a real case, but since it's confidential, I was not able to use the data. So what I did was to generate data by using GenAI, obviously. And so because, as Stefan mentioned, we are used to analyze structured data that comes from customer surveys, but often now you have also some kind of open-ended questions. And so where the consumer is just, describing his feeling about the product, or, describing using text, describing his feeling, right? And so a few months ago, we were just unable to do anything with this kind of data, but now we can try to analyze it. So here there are two parts in this webinar. So the first one is the analysis of a text. So it's a summary. So this is a summary of customer feedback. So I've done that precisely for being sure that we can recover data from a text. So I'm used to use Hellixia for analyzing books and so on, but here I wanted to be sure that we were able to capture the dimension we wanted here. And the second part of the webinar will be focused on the analysis of individual customer reviews, right? So here we have 50 customers. So everything has been, again, generated artificially, but you have used like 2 or 3 variables that have been, qualified as either positive or negative, not neutral. And I have also the last part is about the overall liking of the product, if you will. And at the end of the day, we are going to generate this kind of network. So this is what I call a hierarchical ICI model. So ICI means independence of causal influence. So we are assuming here that all these nodes with, like limited exterior colors, attractive exterior color, like that, have an independent impact on the liking, right? So this allows us to have lots of parents associated with our target node, but without having a conditional priority table that is growing exponentially with respect to the number of parents. So let's start with the first section. So where we are going to analyze, summary of customer feedback. So I'm going to start with by using, the document analysis block here that I mentioned before. So I'm going to generate qualitative graph for understanding the content of this document, right? So I'm going to generate semantic flowchart, causal semantic diagram, knowledge graph, and at the end of the day, a causal Bayesian network. And once I've done that, so I will extract enough knowledge to start the elicitation of the dimension. So I'm going to generate a semantic network. So here, just a note to let you know that what I'm doing here, the way I'm analyzing this data and the way I'm using Hellixia is really a kind of, I'm doing almost exactly the same thing as what we do when we do brainstorming. So instead of doing brainstorming with a set of experts, my experts here are the LLMs that are integrated in Hellixia. So their knowledge obviously is the knowledge that is in the neural network, but also in this document. So we have the knowledge of the LLM plus obviously the document, and then I'm assuming my LLMs are experts, and then I will do the same. I will use the same workflow as the one I'm using when I'm doing brainstorming session with human experts, right? So here, I'm going to start with the first part. So I'm using BayesiaLab 11.6. So it's a version we are going to release hopefully next week. So here, this is, the BayesiaLab startup page where we have the two tools I mentioned before with, the automatic causal network generator and automatic semantic network generator. You have also the media center here, very useful for for accessing the PDF and videos that allows you to learn how to use BayesiaLab. So you have PDF here. So this is, for example, one of the slides of the intro course where you have here a semantic network of our customers, right? So all these bubbles represent a customer, and they are connected by using the semantic operation between the name of these companies, right? So you have the PDF of the courses and also the videos. So for those who have a commercial license of 1 year, you should have access to these resources, right? It's included in the package. So now I'm starting by analyzing my document here, the summary of the feedback of the customers. And so I'm going to Hellixia here, go to document analysis, and choose my semantic flowchart generator. So I have this wizard, so where I can choose among all the engines that we have here. So it goes from OpenAI to Google, going from Meta, Mistral, and so on. And I'm choosing my best, my preferred choice, which is Claude from Anthropic. Then here, this is where I can define what is the context. So my context here, I have two pieces of context. So I have the knowledge file. So this is where I'm gonna associate, the text, right? So here now we can manage, TXT, PDF, Word, Excel, HTML, MP3, WAV. So you have lots of formats that are available. So you have also the list of all the knowledge file you have used so far. And then by clicking on this little eye here, you have a preview of your knowledge file. Very useful because you have to be sure that it has been correctly converted. If you have an MP3, then you just want to know what has been understood by our engine, right? So here, no problem with the text file, obviously. Then the general context. So here I'm gonna, same thing, you have the history of all the context you have used so far. So I'm gonna go with my car narrative synthesis here. Then language, so a large set of available languages. So I'm gonna choose English. And then you have some features for defining the length of the node description, arcs, and complexity, and some option about, do you want to have classes? Do you want to have, so this is a new option, the entity relative location in the text, just to have an idea where is coming or where is located the node in the text, right? And then let's go with OK. So here it's a little bit fast forwarded just to prevent to have to wait too long. So here is my semantic network. So usually, not always, but usually it's like this kind of chain, right? Because it's sequential. And we see that we have one color per node here. And so this is something new for the comment of associated with the art. We had before the color of the comment was so the color of the link. Now it has its own color, and we have two colors that are available now. So we have the top and bottom. So this is something you can check here by going to the rendering properties. And this is very useful to identify what is the parent and what is the child. So the top color is the one of the parent and the bottom is the one of the child. So when you have a huge network with lots of crossing links, it helps a lot to identify the parent and children, right? So here is our semantic flowchart. So we see that the document starts with an initial car exploration. Then we talk about exterior color, interior design, performance, safety system, comfort, digital dashboard, and final assessment. And you see between brackets 70, 100%. So this is where this final assessment is located in the text file. Then I'm going to now create a causal semantic diagram. Right, so same thing, document analysis, almost the same wizard, right? So I'm keeping the same options, and then go to OK. And you can see the name of the file is CSD, just to indicate that this is a causal semantic diagram. So now you see it's slightly, even though the nodes are almost the same, it's not the same organization. So we see that interior design affects user satisfaction, engine performance determines user satisfaction, and so on. So here it's organized, but from a causal point of view, right? Then I'm going to create a knowledge graph. So it's a third type of graph that we can use for analyzing or trying to understand a document. Sorry. And here we see that we have, so it's not causal, right? But we have the core model that features the exterior design, I guess. Exterior color, sorry, contains the interior design, powers engine performance. So you have the label associated with the link here is a verb that describes a relationship, right? So we have all these information that now we start to understand that we are talking about, we have some external dimension, interior dimension, performance, safety, right? And now I'm going to create a causal network. So the first three one were purely qualitative. Now this one is really a Bayesian network, even though I'm not going to use it for probabilistic inference. It's just for, gathering some additional knowledge on this file. So here the target node is the summary of the general idea of the document. So the car, the overall appeal and desirability of the car. And then we have here, so it's a really a causal network here. So we have different parents, exterior design appeals that is defined by the light exterior colors, the dark exterior colors, and the color palette enhancement. So here we can see that it's not only based on the document, because it's a causal network that we have. So we have designed special prompt for that. So here the color palette enhancement, for example, is an action that can be done for improving the exterior design appeal. Same thing for market trends and user demographics. It does not belong to the document, but it's more for having a comprehensive causal network on that. Then we have the interior quality, and then the safety features. And at the very right, we have the performance, right? Where you can see that we have a a red arc here between eco mode and performance quality, because it seems it's a negative feedback from the users here, right? So blue is positive, red negative, and in the comment you have also the causal effect, independent local causal effect of these dimensions. Okay, so we have so far created 4 networks to understand what was contained in this document. So now we start. This is the first step of a kind of brainstorming session with Hellixia here. We're going to try to find what are the dimensions we are going to use in our causal model, right? So for that, I'm going to use a semantic network, right? So I'm still going to document analysis and go to semantic network generator. So this one you are used to see it because I've already presented it a lot of time. So here we are choosing the engines that will be used for creating the embeddings, because now this one it's based on machine learning. So we use Hellixia for finding the nodes and creating the embeddings. But after that, we use the maximum weight spanning tree for machine learning, the correlation between the nodes. So in that case, semantic correlation. So we are going to use Voyage 3. We still use Claude otherwise. The context is the same. And in this version, we have introduced, predefined group of keywords. So this one, for example, domain description. I have selected 10 keywords. So you see characteristic, concept, contribution, element, ideas, and so on. So these keywords should allow you to have knowledge about the domain, right? So I'm going to run the semantic network with these 10 keywords in English, right? And create classes. So with that, it's now creating the embeddings. I have this semantic network where each color corresponds to one specific keyword. And then, so after a little bit of layouting, I have these 15 nodes that have been found, right? That describe really what is contained in the document. So you see on the lower right corner, we see that we have a data set. So this is a data set of embeddings, and all the relationships have been machine learned, right? So it's not the same approach as the first 4 networks we have created that were directly created from the beginning to the end by Hellixia. So here it's Hellixia plus our machine learning features. So here I have my semantic network. So again, additional information. But now, in order to create my ICI model, well, I want to see what has an impact on the satisfaction. I'm going to use another set of keywords, just pros and cons, right? So instead of using my default group of keywords here, I'm choosing cons and pros, right? So I have 2 keywords out of the 165 keywords that are available. And then I'm choosing English, not description length. I set long to extract the maximum information. And I have now 9 nodes. So 2 cons and 7 pros, right? With a bit of layouting. And we see, so we have the advanced safety features, superior comfort, and so on. So these are the pros. Oh, so we have 3 cons, sorry. And then we are going to use these variables as inputs of our causal model, right? So this step was the same thing as having a group of experts where we talk, and we use Biki, and in order to ask each expert, what do you think is important for characterizing user satisfaction? So here, instead of using expert or subject matter experts, we are using Hellixia for identifying this dimension based on the knowledge contained in the LLMs and the text file. So now we have the input nodes, right? So next step will be to define our causal model. And again, we are going to use the ICI structure, so independence of causal influence. Then once we have the structure, we are going to use Hellixia for estimating the priors and also the independent local effects. And once we have this, we are going to have a fully specified Bayesian network that we are going to be able to use for analyzing the impact of each of these drivers. So we are going to build our ICI model. First thing, remember that these nodes have been created by using a semantic network, which means that each node has a data, so we have embeddings, and these embeddings are obviously continuous values, right? So these nodes are continuous and have been discretized into 5 bins of equal frequency. So we need to convert these nodes into Boolean nodes just to know if advanced safety feature is true or false, right? So we go to the tools. Here you have the 5 bins, so we see that it's continuous and with equal frequency. We go to tools and then Boolean conversion to transform these nodes into Boolean nodes, right? So we don't have data any longer, and we have these 9 nodes that have been now that are Boolean, right? And we create our target node. So this is the output of our model, if you want. We set it as target, and then we create our ICI structure. So for that, we select all nodes, we go to tools, independence of causal influence. Then we have this wizard. So I'm not gonna, it would take lots of time to describe what are these ICI models, but here, real quick, we have this input. We are assuming that they have an independent causal effect. So we have to define in this wizard what is the output node. So this is our target here. And then we have to define what combination function we are going to use for combining the effect of all these inputs. So here I'm choosing the sum, which means that I'm going to be able to have negative effect, neutral effect, and positive effect on my target. So this is what we call a mechanistic local effect, because I need to transform these Boolean nodes to have negative and positive effect, right? And the other options are not important today. So with that, I have my structure. So you can see I have a child associated with all these nodes. And then we have these pink nodes here that are sum, where we are adding all these effects into a final sum node that we will map to our target. So let's have a look real quick to the local effect node. So you see it has 3 states, -1, 0, 1, which means that it has, when it's false, we will need to identify it. When advanced safety feature is false, is it negative? Does it have a negative effect, a neutral effect, or a positive effect? And same thing when it's true, right? So these are the questions we are asking to our experts, so either human or GenAI here. So we have automatically created a question here. So what is the independent local effect of advanced safety feature on car overall liking? So we have one of these nodes associated with all these. And then, so this is a final sum, you see, so it goes from -9 to 9. And so it's purely deterministic. So we have the formula here. So this is just the sum of sum 7, which is already another node, plus the effect of the last node. And then if we go to the target, so this is how we map the sum that goes from -9 to 9. We have to convert these numerical values into a Boolean node. So a node that has 2 states here, true and false, right? So here, when it's negative, it's mainly false. When it's 0, it's 50-50, and then it goes to 100% when it's positive, 100% true. So it's a sigmoid that is automatically created here, right? So now we are gonna estimate or elicit the prior of all these drivers, right? And for that, I'm not choosing just one engine, but I'm choosing the engines that are available in my list. So here you see I'm using OpenAI Mini, O1 Mini, Pixtral, Claude Sonnet, Gemini Pro, and Llama, right? So I'm using these 5 engines. So it's like having a group of 5 experts in the room, right? The context is still the same. And my subject of query is the name of the node, right? So in that case, it's going to be what is the prior for advanced safety features, for example, in English. So we are sending that to these LLMs. We have this, sometimes this happens, so there is a timeout here with Llama. So we just do OK. And then, so as you can see, we have new icons associated with our nodes, right? So this indicates that we have some expert knowledge here. Right? So when I hover these icons, I can see the total of assessments, the number of experts that have been involved, and the divergence. So here, no divergence for this one, no divergence for this one, 23%. I'm going to describe what is the divergence in a few seconds. So the darker the image is, the stronger the disagreement is. So here, no disagreement, as you can see. All the experts have given the exact same distribution. 892, and it was not that difficult because it was directly written in the text, right? Then if I go to this one where it's dark blue, so there is a strong disagreement, we can see that in the condition priority table, or in the priority table here. It's when it's yellow, this means that there is a strong disagreement between experts. And here we can see indeed that we have 3 that are absolutely equal, 82, 18, but one that is 82, 18 reversed. And when we look at the comment, it seems that OpenAI just inverted true and false, right? And this is exactly what we have also with human experts. So this is quite funny, right? So what we're going to do here, given that the comment associated with this distribution indicates the opposite, so we are going to fix this manually. So this is something you always have to check what happens behind, because these are just generated. These priorities are generated by using these LLMs, and we know how it works, right? We have the assessment report that allows us to have an access to all the probabilities that have been generated. So we have in this report, you see, you have the node on the left and the experts, the distribution that have been given, a level of confidence, and a comment. So very useful to have this comment, because then we can fix things. And this is also very useful because when we do that in real brainstorming session, yes, you have extra knowledge that can be also super useful for the experts, right? So when it's white in the distribution, the columns with a priority distribution, this means that there is no disagreement. And when it's blue, there is a disagreement. So here we don't have lots because everything is light blue or white, right? And now for having a fully specified Bayesian network, we need to estimate the local effect. So now the question is, we know that advanced safety feature has an impact on the user satisfaction. So we need to estimate this local effects, assuming that all other dimensions are in their neutral state. So what is the effect, the causal effect of advanced safety feature on the user satisfaction? So we have 2 distributions to estimate, one for false, one for true, right? And then, so we are going to use Hellixia for that. We go there. So on the local effect elicitor, we use here the node name and node comment because we have long comment. So which means that we don't need to use the context now, because everything has to be included in this comment, because we chose a long comment when we generated these nodes. And then we are again using all these LLM engines to capture these local effects. Same thing with Llama. We have the timeout for 3 nodes. So when we go, we hover over so we click on this node first to check the priority. We see that for false, no disagreement. For true, it's yellow, so there is a little bit of disagreement. And when you see, so for false, indeed, they are not 100% on agreement, but it's not strong. and there is nothing strange in the comments. Nothing has been clearly inverted, at least. And for true, so this is because of this 2080 that we have this in yellow, right? Because between Gemini and OpenAI, Gemini says +1, 20%, and for OpenAI, the +1 is 80%. So much stronger effect for OpenAI. But at the end of the day, we are using all these probabilities with the associated confidence to compute the final probability distribution, the consensus, if you will. So we have that for all these nodes, this one, no disagreement. And then we can generate the report of assessment. So we have here, so the same thing for the prior, nothing new. And this part is for the conditional, so the local effect, right? So same thing, when it's blue, we have some disagreement, yellow, no disagreement. And the confidence is in green, right? So you can see that when it's for the pros variable, so when it's false, it can have a negative effect. And when it's true, obviously, it has a positive effect that has been estimated by Hellixia. Right? So now we have a fully specified Bayesian network, so we can start to analyze it. We go to validation mode, use our sort target correlation. Then we have automatically all these monitors that have been added in the monitor panel. They are sorted, so the most important variable with respect to neutral information is superior comfort. And the one that has the lowest impact on the entropy of the overall liking is customable dashboard. But when you see the prior, it's not surprising because it's almost always true, right? And then we are gonna create now, analyze it by using a tornado graph, right? So we go to visual, target, posterior, total effect, and we have the tornado that correspond to this graph, right? So the most important, or the dimension that has the strongest range of impact, or the largest range of impact, is advanced safety features. And the one with the lowest one is the light interior maintenance issue. And in the dashed line, you have the prior for overall liking, which is 91.2 here, right? So we close that, and then we can play with the network. So if I set superior comfort to false and striking to false, we have automatically, obviously, an impact on the target node. And now I'm going to use BayesiaLab for generating, the extreme case analysis. I want to see what is the worst case scenario and the best case scenario. So I'm using a genetic algorithm for that. So I'm choosing the state false, choose maximization, and then we're going to find the combinations that creates the worst liking. So obviously the pros will be false and the cons will be true. I just go to my scenarios that are at the lower right corner, choose the best solution, and here in the worst case scenario, the liking is false with 96%. Then I can do the same thing for true, for the best case scenario. Right, so I choose priority state true, maximization. I have the optimization. I go to the scenario file here, choose the best solution, and here we have, when everything, all the pros are true and all the cons are false, we have a probability of liking equal to 98%. Right? So this is the analysis of this network. Right? So we have created a Bayesian network, a causal Bayesian network, by using Hellixia. So now the last step with that is to try, as we can see, that the output was quite optimistic. So because we use by default the sigmoid function that was the output of our ICI generation feature. So here we can try something that is less optimistic. So for example, we can say, well, if it's negative, it's going to be 100% false, right? And even when it's 0, and then it's going to be true only when it's positive, but then I will assume that I need to have four output true to have 100% of liking, right? So I'm just defining that, normalizing these probabilities to, so when the sum of all the effect of my nodes here is equal to 1, this means that I just have 25% of chance to have a liking, right? And to have 100%, I need to have at least an output of 4 out of this 9. So it's going to be less optimistic, obviously. So you see the marginal now is 55%. But at the end of the day, the analysis, when we use the tornado graph, does not change a lot, except obviously the prior, right? The marginal distribution of my car overall liking. But otherwise, it's more or less the same, right? But this is something you also have to consider when you use this ICI feature to check the mapping function and to adapt it with respect to what the experts are telling you, right? So now let's switch to the second part. So we are going to assume that now we have, the open-ended questions that are, so we have one text, if you will, per consumer. So we can have in the same file some kind of quantitative data, but here we just focus for each consumer. We have an output, a brief output here, and we want to analyze it. So you see, it's quite different because the first one was a kind of text that was coherent, and here we have like 50 little texts, right? So we need to analyze all these text to try to extract a useful causal Bayesian network. So we are going to start with the same thing, graph-based document analysis, but this time I'm not just going to use a flow chart and then the semantic network to extract the dimensions, the pro and cons. And then I'm going to use an ICI approach, but this time I want to show you how to build a hierarchical ICI network. And then we go through prior elicitation and elicitation of the independent local effect. And at the very end, we're going to analyze the model. So let's explore these 50 texts. So we use a semantic flowchart. Obviously, I need to change the knowledge file. So it should be in my list that is already available. Preview. So we see the 50 outputs. So the last one, for example, is nothing remarkable, right? We have lots of positive feedback, but not all, obviously. And then, so we can see that everything is okay. General context, we change it to indicate that this is coming from 50 individual user feedbacks. We still are working in English. We go back to all the default settings for the length, and complexity, and we get rid of the entity relative location because here it does not make sense to use this feature. So after a few seconds, we have our semantic flowchart. So it's a user reviews collection. We generate, performance evaluation, interior assessment, exterior feedback, and safety feature review. And these 4 blocks: affect, influence, impact, determines the overall satisfaction, right? So we can see, so this is what I was looking for. We are going to have here more or less the hierarchy of our ICI model. All right. So then we go back to the dimension elicitation, where I'm going to directly find or search the pros and cons, right? So they are already selected, my 2 keywords out of 165 that I'm using for analyzing this text file. Still in English. I want to have the most comprehensive description of the node. And then here I have my semantic network. So again, it comes from machine learning, so by using embeddings. So we are going to need to convert these nodes in Boolean nodes. So we select all nodes, we delete the arcs and go to conversion, node dataset. Then we are going to define our hierarchical ICI model and create 3 latent variables. So same thing as before, we have 5 pros and 4 cons, right? And then I'm gonna go back to my semantic flowchart here to capture these 3 latent variables. This one I don't need it because it's just contain one node, right? So I copy these nodes and paste them in this graph. And then I need to organize a little bit this graph. So I rename these nodes because they correspond to kind of sub network. So it's going to be the performance overall satisfaction, interior overall satisfaction, exterior overall satisfaction. And then, as you can see, it's a little bit fast forward. And so I'm aligning the nodes horizontally, vertically, and to get something quite nice. And then I'm removing all the comments that are associated with these 3 latent variables, because these comments were coming from the other node, so I don't want them from the other graph, sorry. And now I'm gonna have to create 3 local ICI models. So I set my overall satisfaction, performance overall satisfaction as a target node, select the 2 nodes that will be part of this model, go to ICI. I'm going to use the same settings for all of them. So with the sum to get some negative and positive and neutral effect, right? Same thing for interior, ICI, and then same thing for exterior, target node, ICI, generator. And then I'm going to create a hierarchical ICI model. So I create my target node, car overall satisfaction. Then I select the 4 nodes that will be directly connected with this target node. So the 3 latent variable plus my advanced safety features. So I have my local effect associated with these 4 nodes. And now I can go through the elicitation of the root nodes probabilities. So knowledge file, to be sure that I'm going to use these independent reviews to estimate my probabilities. I still have this timeout from Llama. I have my icon that indicates that the probabilities have been elicited, right? And then I can go to the assessment. So I can see that indeed, again, there is something strange with OpenAI here, but this time I cannot revert them because it's in agreement with the comment. So it seems really that it's thinking that 18% of the user found the exterior design attractive, which is not true, but this is the OpenAI output. So now same thing for luxurious interior, just can review, and these probabilities are in agreement with the comments, so I'm not changing them in this webinar, at least. The report, so we went through that already, but just to, so this is for the priors, so there is no dark blue, so it's okay. Right? And then we are going to be able to estimate the local effect of the submodels. So here the thing is that we cannot do that directly. So we have to set to do it submodel by submodel, right? Because we need to have to focus on the target node that is the output of the ICI model. So we need to set each of these submodel sub-targets, if you will. So we get rid of Llama just to not to have any more timeout. And the last step is to estimate this effect of the latent variable plus the advanced safety features. We can review the assessments. And then, so we still have the same part with the prior, and we have the analysis for the local effect. So more or less the same kind of information that we had in the other one, right? With a positive effect for the prompts when it's true, negative when it's false, and reverse for the cons variable. And some when it's false, it just have no effect, so it's neutral. Right? So lots of information in the comments here. And now we switch to validation mode for analyzing our fully specified causal network here. Same thing. So this is sorted with respect to mutual information. And we set the three latent variables as not observable because they are by definition latent. So we set a cost of a negative cost, which makes them not observable. And we can generate our tornado graph. And we see that we have, so advanced safety feature now is in second position, just after the impressive performance. And then we have this nice tornado here. And the last thing I wanted to show you here for this example is the total effect on target. So I can generate a quadrant here by using a standardized total effect, which is the same thing as a direct effect in that case, because we are assuming that they have an independent causal influence. So you see this little triangle, when it's blue and going up, it's a positive effect. When it's, I don't know exactly what is the color, yellow or so, and going down, so this is a negative effect. So we see on the lower left corner the cons, and the upper right corner the pros. And so on the y-axis, we have the effect, the standardized total effect. And the x-axis is the prior of these nodes. Okay? So this was what I wanted to show you during this webinar. So I have written an article on this topic that is available in our website a few weeks ago. So you can directly go to the Hellixia example section in causality, and then there is car evaluation. So everything is detailed step by step. And in this section, you also have lots of examples about philosophy, literature, cinema, and so on and so forth, and also a documentation about the Hellixia features and function. So on that, I want to thank you for your attention, and I hope we are not too late.
Thank you, Lionel, for a most fascinating presentation. I'm glad we will have a recording of your talk so I can try to absorb everything you said at a much slower pace. Anyway, I can see a huge range of new applications with Hellixia, and I look forward to all the conversations we'll have with the BayesiaLab community on this topic. And this is the perfect segue to talk about this year's BayesiaLab conference. I'm delighted to announce that the 2025 BayesiaLab conference will take place at Florida Atlantic University in Boca Raton. So please mark your calendars for June 5th and 6th. I look forward to reconnecting with the BayesiaLab community in such a lovely location. And some of you may be tempted to add a little beach vacation after the conference. You'll certainly find me on the beach after the event. Anyway, the registration for the conference will open on Monday. This concludes today's webinar. I really appreciate your interest, and a special thank you goes to those participants in the Asia Pacific region who have stayed up really late to join us today. Thanks again, Lionel, and I look forward to seeing all of you at a future BayesiaLab event. Have a great day.